Hello there and welcome to this workshop. My name is Valentine. In this workshop, we're going to learn about dimensionality reduction with Python. Dimensionality reduction involves reducing the data that you have in order to use it for machine learning training. So in cases where we want to make predictions, where we want to create applications that make predictions, so for example, if we want to predict prices of houses based on other houses that we have already or we already know about the prices of, so we can create a machine learning algorithm that can do that task for us. But in some situations, if we want to ensure that our machine learning algorithm is as accurate as possible, and also, we might want to use as few resources as possible when it comes to that machine learning training process, then we can use or we can perform dimensionality reduction techniques on the historical data that we would want to use to train our machine learning models on. So yeah, so that's what this workshop is about, learning about those dimensionality reduction techniques that we can perform, which are part of feature engineering, a part of that process that involves preparing data for machine learning training. And hopefully by the end of this workshop, you will be in a position to create far much more, you'll be in a position to apply these dimensionality reduction techniques with the aim of being able to create machine learning models that are able to make accurate predictions and that are able to do so efficiently. All right, let's get first to learn about the agenda. This is the structure that we'll get to use when it comes to this learning experience, getting started with the learning outcomes. After that, talking about what those dimensionality reduction techniques entail, why we would want to perform them. And then get into a practice session where we will apply those techniques using the Python programming language, and lastly talk about the next steps. So getting started, the learning outcomes, by the end of this workshop, we expected to have achieved the following learning outcomes. Let me just reshare that in a few. Do that. Okay. Just a second. A minute. I should have reshared this a while ago. Let me just reshare them again. So by the end of today, we expected to have achieved these learning outcomes. We should be able to define the concept of dimensionality reduction and explain its importance in machine learning. We should also be able to identify different techniques, such as what we will get to learn. There's one that's called principal component analysis and another one called linear discriminant analysis, or PCA or LDA in short, for dimensionality reduction. And we should also be able to apply dimensionality reduction techniques to reduce the dimensions of a data set in Python. What is dimensionality reduction? So this is a process that we normally use in machine learning and in data analysis that entails reducing the number of input variables in a data set. And the idea is to retain as much of the relevant information as possible. So if I were to explain that again in a different way, it would generally entail taking the features or the independent variables that we have in our training data set that we would use to train a machine learning model on, and reducing that feature or reducing those features or independent variables. Initially, maybe in our training data set, we might have 50 records, 50 columns, 50 variables, and when we perform dimensionality reduction, we might want to reduce the 50 variables to maybe 20 or 10 variables. That way we have a smaller data set that still is representative of the original data set, and that means it would still have retained relevant information still from the original data set as possible. And the idea behind this process of dimensionality reduction is to simplify how we are able to work with models. The other thing is that we might want to reduce computational costs when it comes to training. So instead of training a machine learning model on a larger data set, then we can be able to train it on a smaller data set that still would retain as, again, as relevant information as possible that would still be found in the original data set. And the other idea would be to eliminate noise and redundancy. Sometimes we might get to have variables within our original data set that do not necessarily contribute to the prediction performance of a machine learning model. And when we have a smaller data set that is, as a result, multiple variables from the original data set, then in such a situation, we're able to reduce that noise as well as redundancy. These are a few common techniques that we can perform in terms of dimensionality reduction, in that process of reduction of input variables. And there's principal component analysis, which is the common type of dimensionality reduction technique that we can get to work with. There's linear discriminant analysis, there's singular value decomposition analysis, technique. I won't say it's an analysis type of, it's just a technique. And there's also T-distributed stochastic neighbor embedding, that's Disney technique. So those are just a few techniques. There are others that we won't cover in this workshop, but just having an understanding of these ones is just basic enough for you to be able to undertake most basic machine learning projects. Something else to note is that we'll also, after this workshop, after this experience, we'll also continue posting videos about projects, specific projects where we can be able to apply these techniques. And so that is something that you might also be interested in. If you don't find those videos, if you don't get to be notified about those videos, if you're not a subscriber, you could always find those videos in the description section. We'll add them. They'll just cover different projects that we can undertake with regards to these dimensionality reduction techniques. So we'll also go through each and every technique in a short while. So why would we want to perform dimensionality reduction? We've talked a bit, but again, the idea is also to improve performance. Having in some situations, we might end up just having a model that does not achieve our metric of success, and we might try to also apply dimensionality reduction techniques in an effort to just be able to get that performance that we want from a machine learning model. So it doesn't hurt feature engine. It's dimensionality reduction is a feature engineering technique, and it's more like how we would create new data. Like, when we perform feature construction, we might want to create maybe a new variable. We might even want to perform feature scaling. So dimensionality is one of those techniques that we can also perform in addition to those other ones. Reduced overfitting. So we might end up also ensuring that our data, the data that we use for training our models, is actually suitable for the model, in the sense that with, again, fewer features, we are less likely to overfit the training data. So we are less likely to have our model learn so much in terms of noise from the training data, such that when it gets new records, it's not able to make predictions. But when we have data as a result of dimensionality reduction, we end up having a model that has reduced overfitting. Enhanced visualization, using one of the techniques that we've mentioned, that's Disney. We are able to, that's the last technique that we mentioned in the previous slide, we are able to also visualize data in 2D or 3D visualization. So that's also one of the advantages, and just get an understanding of clusters within our data set, etc. Noise reduction, I think I've already talked about. This is also connected to overfitting. So you're able to eliminate less informative features that can also act as noise. Techniques, maybe just to quickly go through some of those techniques that we've talked about. This PCA, which is the most common dimensionality reduction technique. We won't go through the mathematics behind this particular technique, but generally this technique, what it does, it transforms your data into a new set of variables, which are called principal components. And these are normally linear combinations of the original variables. So initially, when you're applying this technique, behind the scenes, what happens is that you are able to find the directions, which are called principal components, where the data varies the most, and you get to now use those principal components within now your new data set, and use those particular variables for training. So you could have maybe a data set with 50 variables and decide to use this method to come up with principal components, like 5 principal components, which will be just 5 different variables that would be representative of the 50 variables, and you can use now this the new data set with the 5 principal components to train your data set, to train your model, and then use that for prediction. But something to note is that, again, when you are also using the model for prediction, you'd also need to transform your new data using this particular method. So you'd also need to find principal component analysis, or the principal components for the new data sets, for the new variables that you're going to be working with, or for the new data that you're going to be predicting. That way, again, you're able to take advantage of this particular technique. We normally use this technique when we just want to reduce the number of features while preserving the overall structure and variance of the data. So we could use this technique for many use cases, and one would be for something like just trying to look at I think something like regression. Like you can use it for regression. You can also use it for classification tasks, but classification normally you would work with what is called linear discriminant analysis, which is the other technique that we also get to learn about. Yeah, so that's it. But also you can also use it, by the way, for clustering. So when you want also to find groups, or to identify groups within your data using the unsupervised learning methods, then you can also prepare that data using principal component analysis and group that data to group the data into just different groups. So yeah, so that's principal component analysis. There's linear discriminant analysis, which we can use to still reduce the variables that we have in our original data set into smaller into other variables, which would now be part of a smaller data set. And we normally use this technique for classification tasks, and it usually focuses on just maximizing the separation between multiple classes. How it works, it finds the linear combinations of features that best separate 2 or more classes that you might have, and essentially projecting the data into a lower dimensional space. By the way, when we are going to be talking about higher dimensional space and lower dimensional space, what we are talking about is, yes, we have this original data set that has quite a large number of variables. That's a data set in a higher dimensional space. But when we reduce now our variables, we end up having a data set that has a lower dimensional space. So that's important to just understand. And we would normally use this discriminant analysis technique when we want just to reduce the feature space. By feature space, we reduce the input variables, that data set that we're talking about, into a smaller one before maybe creating or training a classifier. So that's that technique that we can use during such a time. Singular value decomposition technique. So this is another dimensionality reduction technique that we can use still when we also want to have a reduced feature space or smaller data set for training. And this particular technique decomposes the matrix down. When you are working, by the way, with a data set, before you pass it on to a machine learning model for training, the format that you would have is usually a matrix form, a matrix form. And what SVD does, it decomposes that matrix into 3 other matrices that we can also use now, that we can now be able to also use for analysis. So it could be maybe for model training. So so it just generally breaks down the original matrix into what are called singular vectors. Again, there's a lot of maths behind it, and I won't really go so much into that. This is just for understanding why, just how these particular tools work. But in some situations, specific situations, maybe research situations, you might want to go a bit deeper into that aspect. So this technique just also keeps what are called TOPS, singular values, because once it breaks down an original matrix, it breaks it down into what are called singular vectors and values, and we use those top singular values to be able to approximate matrix, the original matrix with fewer dimensions. But again, the end result, again, when we use this technique is that we end up with a smaller data set that we can use for training. And generally, this technique, we would use it for maybe text data processing, in some situations when we want to perform a specific type of analysis in natural language processing, when we're working with textual data, such as maybe when we want to perform what is called latent semantic analysis, or when we want to perform collaborative filtering in recommendation systems. When we want to create recommendation systems, then we can use this particular technique. So the other technique that we're going to learn, this technique, it's a dimensionality reduction technique, but we don't use it to reduce the data set into a smaller data set. Normally, we use this technique to visualize high dimensional data into a lower dimensional data. So we use it to just visualize high dimensional data. But again, we reduce the data into just 2 or 3 dimensions, and then we map now the outcome within a Cartesian plane. But again, as mentioned, we don't use this technique for the purpose of creating a data set that we use to train on a machine learning model. Yeah, so I think that's something that I've noted. But I had mentioned we use TSNE to, yes, we can. I had this statement that I had mentioned here, but this is normally for just visualization, to just understand how the data set has, how to just understand the clusters within a data set, not normally to create that data set that we need for training. Yeah, so I think that's a misstatement. Don't consider that. That's not correct. So if you want to maybe perform dimensionality reduction, PCA is usually the most common one. You can work with LDA, linear discriminant analysis, when it comes to classification cases, and also SVD for other cases. So if you want to work on natural processing use cases, maybe creation of models that perform specific types of natural processing analysis, then we can look towards SVD. I think it's also important to note that sometimes we might want to perform also all the mentioned techniques and then compare how they perform, how they have an effect on the performance of the model. So you might get in some cases where you are performing principal component analysis for classification models and classification use cases, and you might realize that, oh, principal component analysis actually the results, the feature set that we get and we use for model training actually leads to better performance than in this other case. So I'll leave it up to you, by the way. I'll leave it up to you to just be able to figure out. Our session will just entail to learn how to apply those techniques. All right, so at this particular point, I'm going to ask you to go to the description of this video. And then, oh, not even that, there's one thing that I had not also covered, which is just mentioning where dimensionality reduction comes in. So when it comes to working on a machine learning problem, we would, of course, initially understand the background information, understand the research problem, set the metric of success. Then after that, we import data, explore it, perform data pre-processing, cleaning, feature scaling. Then after that particular step, we would perform dimensionality reduction, model training, and evaluation, hyperparameter tuning, and deploy and make predictions. So our focus is on the dimensionality reduction aspect. Normally, in many cases, this would be part of data pre-processing or data transformation. So that is something to just keep in mind. And you're going to be creating these, applying these techniques, dimensionality reduction techniques, but our focus won't be on the other aspects. Our focus will only be on the first steps. So we won't go into model training and evaluation, etc. That is something that we've covered in other workshops. So at this particular point, pause the video and then go into the description section of this video. Click on that link that says resources link, and it should take you to this page, dimensionality reduction with Python. And then you can click on the sample practice resource, and that's what we're going to be using to go through our workshop for today. All right, so once you have gotten here, so just click on the sample resource and you should get to this particular page. So once you've gotten to the dimensionality reduction, this page, just click on the sample practice resource and it should redirect you to the sample practice notebook. And this is now the sample practice notebook. So if you're an Afterwork member, you can just use the practice notebook. It's just going to contain all the challenges. And you can also have access to the solution notebook. So starting off, let's go through the prerequisites. So I'll start off with importing pandas. Oh, by the way, create a copy in Drive. Just go to File, then save a copy in Drive. It should open a new copy in a new tab. Then you can use that for our work for today. By the way, if you feel like we're too fast in the workshop, you could always pause the stream or the video, and then you can just rewind and catch up from where probably you might have gotten lost. All right, so I'll just open mine in playground mode. You don't have to do that. I'll just open that in playground mode. Okay, so let's get started. Prerequisite. Let's run the prerequisite. So just run anyway. To import pandas, which is a data manipulation library. Awesome. So it should take maybe a few seconds. Okay, so it's already connected. It's okay. It's imported. So starting off, we are going to be working with okay. Let's see what's happening here. We're going to learn how to work with the principal component analysis technique, which we just covered. So I think these ones, I actually put them quite early. I should have put them here, but you can just run this to just import these two classes that we are going to need from these two modules within sklearn, and PCA will use that class to import the code that we need to perform dimensionality reduction with PCA. Standard scaler will just transform our data the way we want. So and to just standardize the data. So let's just run that, which we have. The next thing, let's load the data set that we want to work with. This is the data set, and our target variable may not necessarily even need to, assuming that this is our dex, this is our feature set, the independent variables. We haven't been given a data set with the target variable, but we might want to do to just reduce the data in such situations, especially in unsupervised learning problems. But in our case, assuming that we want to reduce the data set using the PCA technique. So how do we do that? So first of all, we're going to transform the data set and convert, say, category into values, into numerical values. The same case with salesperson region. We'll drop product because we may not necessarily need. So here Actually, we haven't done that for region, but you could always do this the same. We only have performed encoding, which just transforms the values into numerical representations, like furniture would be given 0, etc. Other values would be given other numerical values that are not 0, or just unique ones. So here we just do data preprocessing, and you can preview the data, by the way. You can just say data dot head to just preview the data that you're going to get when you repeat the same process. And you can see here category, we have now numerical representations. The same case with salesperson. Region, we could also do the same thing, but you can actually do it. I haven't done it here. So once we have done this, we just select the data that we want to reduce, which are these columns, and then we preview that data. This is the data that we want to reduce into a smaller data set. And then, but before we do that, we just perform standardization to just ensure that the larger values do not have a significant effect on our model. So we scale the data, and this is now the scaled data. Like for example, for the first case here, 100 has been represented by this particular value, and 20 by this value, etc. Then we now perform PCA, so principal component analysis. We use a class to create an object, and we want to create two principal components. We can decide 3, but here we're just doing 2. And we could always test out on the effect of the number of components on the model performance. So we can create a model with data that has only 2 components, then data that has 3 components, 4 components, etc., and then compare how that performs. But that's something that you can do. But here we're just going to create now that smaller data set that has the principal components, just 2 of them. And voila, this is now the data set that we can give to a model for performance. And we can split it into training test sets, and use that for training and evaluation. So yeah, so that's principal component analysis. I mentioned we weren't going to go into now seeing how we can apply this data set for model training. That's not our focus. Our focus is just to learn the techniques. At this particular point, pause the video and then work on this challenge. All right, linear discriminant analysis. So this is another technique that we can use to be able to reduce our data set. And it's important to note, by the way, you can also indirectly apply the same to regression tasks. I mentioned that for cases where you want to predict or create a machine learning model that's a classifier that would predict a classes or a variable that has that is categorical in nature, we can use this particular technique to create that smaller data set that we can use for training. So in our case here, you can be able to see that we have this data set. Our variable of interest, by the way, is length of stay. Assuming this is our regression, it's a data set that we use for a regression case. So what we might want to do is just to create another variable that will contain classes based on length of stay. So it will contain 0, 1, 2, but that would be dependent on a range, such certain range, like values of length of stay from 0 to 5 would be maybe one class, from 6 to 10 would be another class. So you can have a variable that we can use for a categorical variable that we can use for this particular process analysis, linear discriminant analysis. So here we just performing just our normal encoding, so replacing the gender and diagnosis values with numerical representations, and then we are selecting the data we want to work with. The target variable is y, so which is length of stay, and we decide to now create just a new variable, or we want to create new values which would be representative of the length of stay. So here we are doing what is to discretize the target variable into 3 bins. So the values will have 0, 1, and 2, but they will be represented. They will be representative of the length of stay values. So that's what we are doing here. We are creating a new target variable y that contains 0, 1, 2, and etc. So if I run this, I should be able to see that that's what's happening. Oh, sorry, let me run this and run this again. So the new target variable will contain these values, and for example, 0 will be for the first record, then 0 again will be for the second one, etc. And we store that. We actually don't even create a new variable in our original data frame. We just consider that as y-binned, and that's what we pass to the model. So to be able to use linear discriminant analysis, we import it from a scalar from the discriminant analysis module, and then we instantiate, we create an object, LDA, then we use its fit model. Linear discriminant analysis takes two particular values, or which you can see here, but for PCA just takes the data set, just one. And then here we transform and get now the data that we want, that we can use. It's also, let me just run this. It's also important to note that you do not necessarily need to go through this process for if you have a data set that has a classification or a categorical variable. So this case we don't have, but we're just transforming a regression problem into a categorical or into a classification problem by simply applying this particular technique. But this is just to also just give you an idea of what you can be able to do when it comes also to preparing that data set for that particular case. And then, yeah, and then you can give that model the results of that. All right, pause the video and then work on the challenge. Singular value decomposition, SVD. So we can apply the same. This is almost, it's actually almost the same as the way we would apply it. We would apply PCA. So assuming this is our data set, real estate data set that contains this data, we would want again to get a smaller data set that's representative of this larger one. We perform data preprocessing. Then we transform our data set. Here we have transformed it, but in our case here we didn't, but we might also want to transform our original data set before using it, just to ensure that some bigger values such as height or even total cost do not have a significant effect on how our model performs. So yeah, so here we are just standardizing our data set, and then we use the truncated SVD class from decomposition module, and we set the number of components that we want, and we use the fit transform function to be able to, or method to be able to get the data that we want. That's the reduced data. All right, there you have it. Pause the video and then work on the challenge that we have given you. So there's a challenge for singular for the practice notebook. All right, the last technique, t-SNE. So we use this technique when, again, we want to visualize high dimensional data in a lower dimensional space. So let's load this data set, assuming that we wanted to just understand maybe the patterns or just clusters that may be within the data sets that we have, original data set. So we start off by loading it and transforming the categorical variables. And we can actually even just preview. Let me run this again, which we have here. Then we just select the data that we want to work with. Again, we can still, here we are standardizing the data. You can see price is quite large. Yeah, so we can do that. And then we apply t-SNE. We get the class, get the components that we want for 2D visualization, and we get the results of t-SNE. And then we display, we visualize now those two particular components in a visualization, which could tell us about the clusters within our data and other patterns as well that we might want. So here is the data set that we would be visualizing. This is just a visualization for the data set that we have. All right, so I think those are just techniques that we have gotten to have learned about dimensionality reduction. You can pause the video, work on the challenge for t-SNE. And again, if you want more practice, consider becoming an Afterwork member So once you're done with the workshop, with the practice work, what would be the next thing that we would recommend? The next thing would be to apply some of the concepts, actually some of the concepts that we've learned in the projects that we're going to be posting. So we'll be posting projects after this workshop in consequent days. So consider going through that project. It's actually 3-day project. You can do those 3 projects and apply the same. We will be walking you through that on those particular projects. If you don't find those projects at the end of this video, you can just have a look at them in the description and see how you can apply them. So that is something that we would recommend. Apply what you have learned in real life projects. Aside from that, the next thing that we would recommend is to ask you to maybe think about now, aside from learning about dimensionality reduction, which is a type of an unsupervised learning technique. So there is clustering, which is one of the supervised learning, unsupervised learning techniques. There's now dimensionality reduction. You can also get to now learn about market basket analysis, which is also another type of an unsupervised learning technique that may come in handy within your line of work. So the idea is just to have ideas on just what are the techniques that you have at your disposal when it comes to creation of solutions, particularly data or related solutions, and get to learn about how to apply them. And yeah, so that's generally what would be our recommendation. I think that's it for this workshop. If you did love this learning experience, you thought it was valuable, and you'd want to see us continue doing the same, just give this video a thumbs up. And if you'd want to be informed when we also post those other future projects that come after this workshop, be sure to subscribe. And all the best in your learning journey. Bye-bye.